Okay, hello everybody. Today we are going to talk about the time discrete Solow model. We already learned a lot about the Solow model in one of our last lectures, but today we have a special lecture, which is the discussion of the time discrete Solow model. So our topic once again is still growth theory. So we are talking about the long run in the economic growth perspective. And that is the Solow model. That is a model we already learned in continuous times. And today we do the same, what we did in one of the previous lectures, just in discrete time. So the lecture is structured in two parts. First, I will start with the key assumption, once again, of the time discrete Solow model. And then we do the derivation, which is bringing all the conditions in one equation. And then, this time, I will try to show you how to simulate, how to illustrate curves in the Solow model by an Excel program. And that is a new part in particular in comparison to the continuous time Solow model, because the time discrete Solow model allows us to really simulate the adjustment process over time. So let me start with the first part, which is once again thinking about what are the building blocks of the time discrete Solow model. And as you can see from this slide, the four building blocks here are very similar to the building blocks and the assumptions we used already for the continuous time Solow model. So the key difference, basically, if you look to the first point, the production function, you see the production function consists of capital and labor. Well, the only new point here is now that I assume that the A, the technology factor, is in front of the labor factor, which is called effective labor, A times L. So this is a slight difference, but not the key difference in the time discrete Solow model. The second condition, as you can see, the closed economy assumption is also the same as we discussed already in the continuous time Solow model. Its saving is equal to investment. So no difference here. The same is true for condition 3, that we assume a certain saving function. It's the same as we already used in the continuous time Solow model. So the saving function is just the propensity to save, this little s, times the output or income, y. The key difference, however, is in condition 4. Here we have a difference in comparison to the continuous time Solow model, what we already discussed in one of the previous lectures. So in continuous times, we wrote the condition 4 as follows. We said the change of the capital stock over time, which is the time derivative indicated by a dot, is equal to, well, it increases with investment and it decreases with capital depreciation. As you already know, delta is the depreciation rate. So this was equation 4 or condition 4 in the continuous times Solow model, as we already discussed. But now we discussed the so-called time discrete Solow model. And in the discrete sense, there is no derivative. So the derivative is now the change of the capital stock over time. So I erase the derivative and now substitute in here the change of the capital stock over time. So capital stock in t plus 1 minus capital stock in period t. This is the change of the capital stock over time in discrete terms, period t plus 1, period t. If t plus 1 and t is very close together, that is what we call continuous mathematics, then this gets the derivative, this kt dot. But now we have explicitly this time difference because we are in the discrete case. So the key difference to the model we already discussed is condition 4, that we have here the difference and not the derivative. So now what I have to do, well, very similar to what we already did, we have to combine condition 1, 2, 3, and 4 in one equation. And at the same time, we have to transform our model into per capita units. Can I remind you again about this per capita definition? Well, Per capita, we use the lowercase letters. Per capita output is defined as absolute output, YT, divided by labor, LT. But now take care. In this case, because of a slightly different assumption of my production function, we have to divide by effective labor, which is AT times LT. So now the per capita is defined by Y divided by A times LT. And the same is true for the capital labor ratio, the small k. That is also defined as the big K or the capital KT divided by, not just by L, by effective labor, by AT times LT. So these lowercase letters indicate the per capita variables, as we already learned in the continuous model. The only difference, again, now we assume that it's not just divided by LT, it's divided by A times LT, because I have a slightly different production function in this example. So now let me come back to the derivation. So let's combine all the conditions 1, 2, 3, and 4 in one and write the model in the end with the lowercase letters, the per capita variables. That is our ultimate goal. So how can we do this? Well, in this case, I will start as follows. We know that the macroeconomy is a circle, right? And the key equation is the income expenditure identity. That is what we already learned in the first class of this macroeconomics course. So we wrote YT, total income, is equal to consumption, investment, and then we said plus G, government spending, plus net exports. However, in this case, there is no government, right? In this simple model, there is no government, therefore there is no government spending, and there is a closed economy, there is no export and import. Therefore, we stop here. So this is the income expenditure identity in a closed economy model without a government. So next, what I do, well, I basically transform this income expenditure identity into per capita unions. So I multiply the whole equation by 1 over A times LT. Yeah, that every part gets into per capita. That is my ultimate goal. So I do this, and then you see, well, Y divided by A times LT gives me the lowercase YT. And then C, the consumption divided by ALT, gives me the low c, the consumption per household or per capita. And then for the investment, I do it a little slightly different. First of all, I also have here A times LT in the denominator. But for investment, I use now condition 4. You see, here we have investment, and I bring this part on the other side, and then I substitute in here this equation. So what do I have if this is on the other side? Well, I have KT plus 1, and then I have minus, and if I factor out the K, if this is on the other side, is then 1 minus delta KT. Yeah, if you bring this on the other side, it gets plus, and minus is also plus delta KT. It's just factoring out the KT. Okay? So what I have here is investment, and I just substitute the left-hand side in here. Okay, that is good so far. In the next step, well, I just simplify now this a little bit. Consumption. So what is consumption? Well, consumption, you know, is the opposite of saving. So if you think about my saving function, you know the saving function, condition 3, is saving times my income. So what we can say consumption, well, consumption in the end is 1 minus the propensity to save times income. Why is this the case? Because the propensity to save plus the propensity of consumption adds up to 1. So if we subtract 1 minus the propensity of saving, you can say this is the propensity to consume, the little c. Yeah, and then we have a consumption function, which is c times income. So for consumption, in other words, I can substitute 1 minus s times per capita income, which is the first part. So that is 1 minus the propensity to save times income. Plus, now I erase this here. I simplify now the second part. So what I will do here, first of all, I split it up in 2 parts. You see, that is one part minus the second part. So we have kt plus 1 divided by at times lt. So I keep some space here. And then we have the second part minus 1 minus rho, and then I have kt divided by at times lt, which is this divided by this. This is just a constant in front. Well, as you already can see, this is quite clear. Kt divided by effective labor, this is my little k. This is the capital labor ratio now again. The problem here, if you take a look to this, it's also kt divided by a times lt, but the problem here is that that is kt plus 1, and we divide by a in period t and l in period t, so that the time period does not match. So we cannot really say that is the small k. But there's a simple trick to transform this in the right period. So I extend this just by dividing by at plus 1 on top and on the bottom. That is what I can do, because I can also cancel it, then it's 1. So I just write at plus 1 lt plus 1 in the numerator and in the denominator. And now what we have here, it's k in t plus 1 divided by a in t plus 1 and l in t plus 1. So this is also the little k, but in t plus 1. So this is my k in period t plus 1. Yeah? So here the time periods match, and it's k divided by l, it's the same time period, and therefore we can use again our definition for k just in the next period, t plus 1. The question is now, what is then the remaining part? Maybe I circle this with another color. So what is this here? Yeah? Well, this is what I have to tell you in a minute, but let me first write down what we already have. So what we have on the left-hand side is my yt. Then we have 1 minus the propensity to save times per capita income, plus here we have the little kt times this orange fraction, which I just copy for a second, and I tell you then what it is. And then the last term we have is 1 minus rho times also my little kt. So now we have to, or I have to talk about what is this fraction. Well, it turns out that behind this fraction is a population growth rate and the growth rate of effective labor. So let me remind you, what is the growth rate? How have we defined the growth rate? Well, the population growth rate in the Solow model, what we already discussed, we used always the little n. And the little n, as I already told you in one of the previous lecture, is the change of the population, the labor force, in period t plus 1 minus in period t divided in period t. Yeah, the change of my variable divided by the variable is always a growth rate. So if we take this as a growth rate, well, we can once again simplify this. That's this term minus this term. So it's L t plus 1 divided by LT minus LT divided by LT. Well, that's 1, obviously. If I bring the 1 on the other side, then I have 1 plus n is equal to this fraction, LT plus 1 divided by LT. So now we have the fraction LT plus 1 divided by LT is nothing else as 1 plus the population growth rate. Take a look what we have here. LT plus 1 divided by LT. That is the right-hand side. So the right-hand side, this fraction, is 1 plus the growth rate. So this is equal to 1 plus the population growth rate n. And the same holds for my A. Yeah? I can set up my A is the change of effective labor over time. Same definition as I did here. Simplifying, you will see that this fraction is 1 plus the growth of effective labor, this little a. So in other words, I can simplify these two fractions in 1 plus a times 1 plus n. So let's write it down. So still we have here yt, 1 minus s, yt, plus, yeah? Now I have 1 plus a, 1 plus n times this kt plus 1. I just switch the order, which is possible because they're all multiplied, minus this term. Okay, that's almost finished. Just one line, and then I have the expression I was looking for. Well, I was looking for an equation that is representing the time discrete Solow model in per capita variables. You see all the y's and k are now the little k's and the little y, so we are in per capita. We have used already all the assumptions, and I was looking for an equation that gives me, in the end, the future capital stock, kt plus 1, given on the variables today. So when I rearrange now this equation, that on the left-hand side, I just want to have kt plus 1, which is the capital stock in the next period. And on the right-hand side, I just have terms based on today, period t, right? So that's possible. I just have to rearrange this equation or this line that on the left-hand side is just kt plus 1, and on the other side there are all these terms with kt or yt. So let's do this. First, I bring this term on the other side. Then you can see we have yt here and 1 yt here that cancel. This minus then gets a plus, so we will have s times yt if I move this on the other side. If I move then also this on the other side, this minus turns into a plus, so it's 1. It's then plus 1 minus kt. So this is now on the other side. This is already on this other side. So the only term on this side is this. Well, as I already said, I just want to have k. So if I divide then this by 1 times a times 1 plus n, so if I divide the equation by these two terms, then they pop up here. Yeah? They pop up here on this side. They're 1 divided by n and 1 times 1 plus n. Yeah, and then what remains is the kt plus 1. And that is the equation I was looking for. Why? Because here I am now able to compute the capital stock in the next period, t plus 1. And you can see the k and the income is just dependent on what we know today. That's the period today, t, and that is the future, t plus 1. And this allows me to simulate now the Solow model, because this is the number or the data we have, and we can compute, based on this equation, the future capital stock. And that is what we actually do in the next step. So we try to simulate the Solow model based on the current data. We find out the future capital stock and the future output. Well, there's just one point I have to add at that step. So what is this YT? Well, you know, from my first condition, YT is a production function behind YT. Maybe I erase a part here. So my capital YT is a production function dependent on capital stock and effective labor. This is my condition 1. And what I can do, obviously, as we already did in the continuous time Solow model, we transform also this production function into the per capita production function, which is in the end the little f dependent on the capital labor ratio. If I divide this equation by A times L. So I will get the per capita production function. And if I assume there is also technological progress, right, then we usually also write a certain factor, A, or we can use another letter because we use A for effective labor in this case. So let's use for technology maybe the letter T. So I have a technology parameter times my production function per capita. So in other words, I can substitute in here for this little y the production function per capita times my technology parameter. Due to the fact that in my Excel I have not the factor t, I also use the factor a here. I will do it here as well to make it similar to my slides. So it's in the end a times the production function per capita, which is dependent on the little k. And now we are ready, because again, we have kt here in period t today. We have the kt period t today here. So that is all numbers are given today. We know the labor growth rate, we know the technological growth rate, we know the propensity to save. Now we are able to compute the capital labor ratio in the next period in kt plus 1. So let me now illustrate this on the slide with an Excel spreadsheet. Okay, so now you can see Excel, which you all know, and here in this Excel spreadsheet I have implemented the time discrete, what we call deterministic Solow model. Deterministic just means there is no stochastic, there is no shock and anything. It's just discrete and deterministic, so no stochastic or random impact in this framework. And as we already know, the Solow model consists of certain parameters. Well, there is this population growth rate, this little n, for instance, here. There's the saving rate, there is this technology factor, there is this delta, which is the depreciation rate, and we have this alpha here on top. Well, the alpha, if we assume a production function per capita, Cobb-Douglas, you know, that is A times kt alpha. So this is if we just assume an explicit production function, we also have this alpha parameter. Yeah? And here I have numbers for these parameters. Yeah? I assume that this alpha is almost a third, so it's 0.36. In the beginning, I assume population growth is 0. We can change, obviously, later on these numbers. The propensity to save is 36% or 0.36. And the depreciation rate is 7.5%. Or 0.075, in other words. And the technology factor is assumed, the capital A, as 5. And this little a, which is the growth rate of technology or effective labor, is assumed at 1%. So now, what you have to do, first of all, take a look to this formula. Well, this formula is the capital stock in t plus 1, which is saving times A times the production function per capita plus 1 minus rho plus K divided by 1 plus A, 1 plus N, 1 plus A. If you compare this again with the equation we derived, you see that's actually the equation we already derived 5 minutes ago. Yeah, that's my S times A production function, the depreciation term divided by 1 plus A, 1 plus N. That's the same. So what I do now here in this spreadsheet on here below is actually I just implement this formula into this spreadsheet. So let me explain this. So first of all, in the first column, so here you see time periods. That is the time step. So we started in period 0, 1, 2, 3, and 4. Yeah? And then we assume that the population growth is, so population is 100, and I assume there's no population growth, therefore population stays always at 100. Well, if I change this to, for instance, 0.1, you see population is growing by 10%. 100, next period 110. So this is, you see immediately that if I change the population growth rate, then the population is growing. But let me go back for the beginning, assume there's no population growth rate. So once again 100, and you see population then stays at 100. Then here I assume that the capital stock today is 20. Yeah, 20 euros, you can say 20 million, 20 billion, does not matter, it's 20. So, and now what I'm going to do, I compute the capital stock in the next period. Yeah, this is the capital stock in period 0, and now I will compute the capital stock in period 1. Well, to calculate this capital stock, I use this formula. Because this formula allows me to find the capital stock in the next period, in 1, if this is the capital stock, 20 of period 0 here. So let me click to this cell. Yeah? And then you see this formula. And this formula just links these different cells according to this formula. So let me show this. First, we have here S and this A factor. Well, the S is in cell C17. That's the S. And I just link this times the A. The A factor is in column C, cell 21. Times the production function. Well, the production function, as you know, is dependent on my capital stock of the previous period. The capital stock in the previous period is the cell D33. That's my capital stock of the previous period to the power of alpha. And my alpha is in cell C15. And that is this. So what I did here, in other words, I just linked all the cells according to this formula to compute the capital stock in the next period. Yeah, we can go on. Plus 1 minus the depreciation rate. 1 minus depreciation rate is in this cell, which is C20, times capital stock, which is once again this cell, divided by 1 plus N, which is C16, times 1 plus A, which is 24, C24, this cell, as you can see in blue. So what I have here in this cell is nothing else as this formula. And this formula, the right-hand side, gives me then, calculates by this spreadsheet program, the capital labor ratio in the next period. So that is, given my parameters, around 23.5. And then I just copy-paste this formula for all the time steps here, for period 2, period 3, and so on. And you see I did this until period almost 200, or more than 200, 220. And what you can see here at the end, maybe let's take a look here at the end. Well, at the end you can see the capital stock does not change. So when we are close to our steady state, what we already discussed, When we are close to our steady state, then the capital stock does not change. And that is what you can see here by this calculation. We are now in equilibrium. We can go on, but the forces moves us to this steady state, and then nothing changes. And that is what you can see here in the numbers. So the number does not change at some point. And that means we are in equilibrium. We are in steady state. So let me go up. Okay. So this is, by the way, the difficult step, right? The other columns are not so difficult. Why? Well, here in this column, I calculate output. What is output? Well, output is A times K to the power of alpha. So obviously what I have here in this cell, if I click here, it's the factor A. Well, I have to go up that you can see this. It's my factor A, which is the cell C21, times my K. Well, the K is this cell to the power of alpha, which is cell C15. And then we have output. That formula computes my output. And then I copy-paste this formula down. That gives me output. And you see also the output increases over time as the capital stock is increasing. But when the capital stock stays in steady state, when the capital stock is constant, you see the output obviously here on the bottom is also almost constant and does not change. Yeah? So in the beginning, when we have this dynamic adjustment, output is increasing with capital stock, but in equilibrium, it is constant. Well, the same is relatively simple for the saving function. What is saving? Well, saving is the propensity to save times income. That is my assumption 2. Yeah? Assumption 3. Saving function is saving times income. That gives me my saving. And consumption is the opposite. Income minus this amount, which is calculated, gives me this. And the final column is output growth, which is just the change of output over time. So I will upload also this spreadsheet on our e-learning platform, and you can then take a closer look to all these formulas in this spreadsheet. But now let me show you the curves. That is obviously more interesting. So in the first graph, I illustrate the adjustment of capital and the adjustment of output over time. So let me show this graph. So in this graph, you see the adjustment, the red curve of the capital stock over time, and the gray curve is illustrating output over time. Output is here on the right-hand side, and on the left-hand side is the capital stock. And on the bottom, you see the time steps, right? We start in period 0, then we compute the capital stock in period 1, period 2, and so on until period 2020. And what we have seen in this column, well, at the beginning, the capital stock is growing and growing and growing. And unless we are close to our equilibrium, then the numbers are almost same. Yeah, they converge to our steady state, to our equilibrium, which is here close to 120. These are the numbers in this column on the bottom. For capital, red, and for output, well, think about the output started around 14 something, and then it was growing. It was starting out around 14 because this is here on the right-hand scale. And then we were growing until around 28 in output units. So can I show you this again? So output started around 14, yeah, capital around 20. And if we go down, you see the output here at the end of this is around 28, yeah, and the capital converges to a level of 118. So if we go up and look again to my graph, you can see actually this is a pattern over time. Capital starts at 20, we are going along 118, and output starts around 14, and we are converging to 28. So what you can see here is the adjustment of the Solow model over time. What we talked about last time also graphically in the Solow model. This is the adjustment or convergence process. Well, you can now plot a similar graph, which I did here, for consumption, which is just the other column in my spreadsheet. Yeah, and you can see also consumption. In the beginning, consumption is growing and growing, so you consume more. And when you are in steady state, then consumption slows down and you stay at a certain level, which is here around close to 18. And you can also illustrate the growth rate, which is, if I go to my, so that was consumption here. And now I illustrate this column, yeah, which is the growth rate. And here's the corresponding graph. So in the beginning, when the convergence process starts, growth is very high, as you can see. And when we are very close after some time to our equilibrium, to our steady state, growth is almost zero in per capita units. Yeah? So we start with a high growth, capital stock is growing, output is growing, consumption is growing, and then we are converging to this steady state level of capital and output, and growth is converging to almost zero, which is here, this horizontal line. And you see, the longer it goes on, the longer we are closer to the steady state, we have no output growth in per capita units. So now you can see from this simple spreadsheet program that it's not too difficult to simulate the so-called time discrete Solow model. At the end of this class, I just want to calculate and show you some final point. In this box of this spreadsheet program, you also see the so-called steady state numbers. So that is when we are really in steady state, in equilibrium, right? And we know that is the last number, almost the last number in my column. For capital, it's around 118, yeah, 117.9. For output, it's close to 28, 27.8, yeah, and so on. And I want to give you a formula, which is, by the way, also here in this cell. So if I click here, you can also find a formula to compute these steady state variables. Well, you can take the numbers from the bottom of this column, but you can also compute this. So let me show you how to find this steady state formula. That's my final point for this session. We start again with our final box formula, which we used here. And now we assume we are in steady state. And in steady state, you know, the capital stock in period t plus 1 is the same, almost the same, as we already learned from this simulation, is almost the same as the capital stock in the previous period, and so on. So we can say the capital stock is constant, it has a certain level. In my case, the 117.8 or 9. Yeah, it's constant. So let me now use this assumption, steady state assumption, and instead of kt, well, it's now in steady state. It's now in steady state, yeah, and this is now also fixed in steady state. Moreover, I substitute in here the explicit production function. So I substitute in here for my production function this k alpha steady state to solve this explicitly. So k steady state alpha. And now I have a formula which is dependent on k steady state. So what I have to do to find this k in steady state, I just rearrange the formula that at the end I'm looking for k steady state is equal to a certain term here. And this term comes from this equation. So let's show you how to obtain this. Well, first let me move this on the other side. Then I have 1 plus a times 1 plus n times k steady state. So 1 plus a times 1 plus n times k steady state is equal to s times a k steady state alpha plus one, the depreciation term, steady state. Okay. Then let's also bring this term on the other side and factor out k steady state. That looks then like this term. So we have 1 plus a, 1 plus n. Then this is plus. If I move the whole term on the other side, it is then minus. And I bring the k steady state outside, right? It's k steady state for this and k steady state for this. On the right-hand side, we just have this term. Next. Well, that's already very good because I have k steady state here and here. So let me bring this k steady state alpha on the other side. And at the same time, the term here in front, which is multiplied, on the right-hand side. So what do I have then on the right-hand side? Well, I have s times a. This then here down, which is 1 plus a, 1 plus n, minus 1 plus delta. Yeah, that's this divided by this. And then I have here k steady state. If I bring this on the other side, well, this is like k1. And if this comes to the other side, then this is minus alpha here. Now that's just the law of exponents. Yeah, this on the other side brings me 1 minus k alpha. And now we are already finished, right? I was looking for k steady state on the left-hand side and anything else on the right-hand side. Only this 1 minus alpha is here on the left-hand side. So let's bring now this 1 minus alpha also on the other side. Well, how can I get this? Well, I just multiply in the exponent with 1 minus alpha. Then this cancels, but obviously then it pops up here. Yeah, and here I then just have k steady state is equal to this term exponent 1 over 1 minus alpha. And this formula allows you to calculate immediately the out per capita labor ratio in steady state, in equilibrium. You just have to compute saving rate times technology divided by population and effective labor growth, depreciation rate, and the alpha. And that is actually what I did here in my spreadsheet for these steady state variables. I just implemented, if you click on each cell, this formula, and that calculates then the final steady state, the final output, which is in the columns below just the simulation where you can do it in an iterative way. You compute it for many steps, and then you see at the end of the column, well, it stays constant. That is my steady state. But you can also find the steady state directly by solving the model in our steady state and finding this formula. And that formula then gives you also the final steady state levels. Okay, so that was all for today. That was a discussion of the so-called deterministic time discrete Solow model. I hope you have seen the similarities to the continuous time Solow model we already discussed. The new element in this example was, well, if we discuss a discrete model, we can find a formula that can be easily implemented in a spreadsheet program like Excel, and then you can also simulate this adjustment process, this dynamic process over time. Okay, bye-bye.